Okay, I started the recording. Hello YouTube, it's time to dive into day 14. Yesterday, day 13 was pretty harsh. Let's see how today will go. So as your ferry approaches the seaport, the captain asks for your help again. The computer system that runs this port isn't compatible with the docking system on the ferry, so the docking parameters aren't being correctly initialized in the docking program's memory. After a brief introspection, you discover that the seaport's computer system uses a strange bit mask system in its initialization program. Although you don't have the correct decoder chip handy, you can emulate it in software. The initialization program, your puzzle input, can either update the bit mask or write a value to memory. Values and memory addresses are both 36-bit unsigned integers. For example, ignoring bit mask for a moment, a line that says like mem8 equals 11 would write the value 11 to memory address 8. Okay. Is this important that it's 36-bit? I think it's important because we are applying the mask, and it's basically saying we're applying the mask in a non-ambiguous way. Because like if this was a, I don't know, a U8, then you would probably have to wonder how it aligns. Maybe not, I don't know. But in any case, it simplifies things, I guess. I hope we are just not going to think about like overflow semantics and wrapping operations on 36 bits specifically. Although if so, I think Zig would help, because we can create a 36-bit unsigned integer. Like I just write a U36, boom, I have my U36, which is pretty neat. But I hope I won't have to use this here. So for example, ignoring this for a moment, blah, 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 okay. The bit mask is always given as a string of 36 bits written in with the most significant bit on the left, least significant bit on the right. The current bit mask is applied to values immediately before they are written to memory. So a 0 or 1 overrides the corresponding bit, X leaves it unchanged. That's a really weird bit masking system. Okay, so X is like neutral, so it's not an OR, it's not an AND either. Is it like a weird combination of stuff? No, because so if one, like these are overrides and X is nothing, so you can't represent this thing as a normal bit mask operation, I believe. Maybe. Actually, maybe you can decompose it somehow, but in any case, let's not waste time thinking about this. How long is the advent of code site up for? I think it never goes down. You can access past years advent of codes math if you want to, so I think it's always going to be there. Or at least, you know what I mean, like they're not taking it down on purpose. So this program starts by specifying the bit mask. The mask it specifies will override 2 bits in every written value. So yeah, so you try to write 11, but then these bits get flipped and you're gonna end up writing something else. You try to write 101, but then these bits get flipped and you're gonna end up writing something else. You try to write 0, and even if you try to write 0, you'll end up writing, I don't know, 1, 2, 3, 4, 5, 6, 7, oh god. 64? 128, I guess. Wait, but this starts from 0, so it's actually, yeah, it's 64. Okay, so you try to write 0, but you end up writing 64. Oh yeah, baby. Okay, so I'm gonna skip this. I think it's pretty clear, right? We just need to do this weird masking to whatever value we're trying to write. These are base 10. This is binary, this is base 10. So 64 written as 8 instead, overwriting the value that was there previously. And we start at 0. We start at 0. Is it written somewhere? Oh, the entire 36-bit address space begins initialized to the value 0 at every address. So nice, everything is zeroed. In the example above, only 2 values in memory are not 0. 101 and 64. Okay, that's the result of the operation, producing the sum of 165. So what's the sum of all values left in memory after it completes? And this is my puzzle input. Oh shit, and the mask changes over time. So we have mask redefinitions. Cool. Okay. Let's do it. Also, this address space. So here's an interesting thing that I'm noticing by reading the input. There are a lot of addresses. So memory is probably best not represented as a straight up array, but I think we kind of want like a hash map, I think, for this memory. Because we want a hash map because there's going to be a bunch of holes in there. So that's one thing. The mask needs booleans are not enough. We need 3 states, so we need an enum. We need 1, 0, and do nothing. And then I guess it's just a matter of doing the job. So let's get started. Actually, let's copy the input. Let's go in Sublime, AOC, new file, day 14, also new file, save. I don't know. Let's call it bitmap.txt. It's not a good description on what's inside the file, but I think that's the name of the theme of this exercise. So I guess bitmap is unique enough of a description. So const. Oh, you know also what I haven't done that I want to do. Let's try to quit Sublime and let's see if reopening it gives us Zig. Oh yes, we now again have Zig FMT support. So it just needed to be restarted, which is nice. So const data equals embed file. Path is bitmap, please Sublime, txt. Oh yes, we're making business with Zig format. Okay, I guess we need to get parsing. How do we do the parsing? I think we want to tokenize on these parentheses, spaces, and new lines, but we need to know how much to skip. So I learned how to use tokenize, and now nobody can stop me. std mem tokenize data delimiter bytes is gonna be okay. Let's take a look. Open square bracket, close square bracket, space, equal. Oh, nice, and then new line. This feels like, this is so nice. It feels like cheating. This is so nice. This is so fucking nice. Okay, so now we can scroll through the text. Ouch, though. Ouch. How do we know when we encounter a mask? So tokenize by itself doesn't allow to really know when we get to a mask. But I think we can make do either way, because with the current system we first tokenize mask. So I want to see if tokenizing a mask line and tokenizing a mem line is compatible. And I'm gonna try to give a definition of what I mean by compatible as I go. But here's the idea. I want this to allow me to write one algorithm that can distinguish the two cases, even though tokenize is not like checking if we start with mask or mem. Although actually I could do that. I could tokenize by line, check if it's mask or mem, whatever. Let's see if we can do better. So if it's this line, I get mask. If it's this line, I get mem first time. Second time, if it's mask, I get this because I'm gonna skip this space. I'm gonna skip this equal. I'm gonna skip this space because they're all delimiters, and tokenize goes through them. It doesn't give you empty strings. It runs through all the delimiters, and it's gonna give me this slice here, while this is gonna give me this slice here. And at this point, I can just check, is this 36 characters long? This is never gonna be 36 characters long. And if it's 36 characters long, I'm in a mask line. If it's not, I'm in a mem line. Boom, done. So while it.next well, let's call it token, I guess. So we have our token. Also, you know what? Here's another thing that you can do. Let's just check the token. This is another super easy thing. Is the first token mask or mem? And I know in which case I am. You know what? We could probably do the thing that I just said with the by checking the slice length, but god damn it, this is so dumb. Let's just check the token. If std, the first token, I mean, of a line, mem dot equal u8 token to mask, in this case, else expected, yes. So if we're in the mask case, we need to set the current mask. So also I want to take half a second to think about what is the next exercise going to tell me. How is it going to try to fuck me? To be honest, I'd line tokenize and make a state machine. You're a monster. I know. So how is this going to fuck me? I wish I knew. I don't know. I think something is gonna modify the masks as you go through. Whatever. For now, you'll never guess. Oh, damn it. Okay. So var mask is an array of 36 enums. The enums can be 1, 0, nope. And actually, this is the type, and we get we start with a good chunk of garbage memory. Expected test comp time. Oh, you know what? There is no dot when defining enums. I don't know why I like adding dots in the definition. So I love garbage memory. So let's start with garbage memory. Now, if it's mask, we set it. So I guess if it's token mask, then we do for it.next dot question mark. So we grab the text token, which is going to be the mask itself. We're going to get a bit, right, of the bit mask. And we also want a index. And we're going to do mask index I. It's going to be something. It's going to be switch bit. And in the one case, it's going to be dot one. In the 0 case, red arrow. In the 0 case, it's going to be dot 0. In the X case, is going to be dot not. Any other character, panic, sad face. And that's it. Boom. And this is the mask case. Now, main case. M case. This is the address. This is the value. So const address is it.next question mark. Value is the next thing. Right? Yeah, there is nothing else. And now we have to write this stuff. So we need to manipulate the value and then modify our memory model. So what's our memory? As I said, space seems wide, so let's use a hash map. Memory equals std.hash. We have also array hash map, which is a hash map that makes it that should be more efficient to when you want to iterate over every element, which is what we want to do at the end. So I'm going to use an array hash map. So the type is going to be the key is going to be a SUSY. Value is going to be a SUSY also. No. Oh god. Okay, the hash is going to be, I don't know, it's just, oh, it needs to return a U32. Okay. That's annoying. I think I want a auto array hash map. Okay. Let's make it easy. Let's make it easier on ourselves. Oh, and I close my window. No, full screen again. Yeah. So I don't want to specify the hashing function and everything else. Like I want just the obvious dumb stuff like store hash or whatever. No. So type the key. The key is a SUSY. The value is a SUSY, and we are done. .init, and I think it needs an allocator. So let's steal an allocator from here. Okay, so we have the mask, we have the memory, we have this thing. Value needs to be changed. So value. So for each bit in mask, right, which is actually like an operation and an index, if well, we switch the operation, if it's not, do nothing. If it's 1, if it's 1, you do value. Value equals value. I think it's value. So if it's 1, it's value plus equals 1 shifted left I times, I think. Oh, there's no double arrow. No, yes, there is double arrow. Let's check this. So let's say that I have, I don't know, I have 5. And I want to edit a 1. So I do 5 plus, oh, yeah, I do 5 plus 1 shifted 0. Yeah, shifted 1 gives me 7 because I added a 2. Gives me 13 because I added an 8. So yeah, is this it? You're just overriding stuff. There is no reminder or anything that we need to do. Like if a 1 was there. No, I think I'm doing something stupid. Because if, oh god. Ah, this is stressing, the bit thing stuff. So annoying. I can't just add, because if I add and that bit was already 1, then I should not add. So add is not the right operation. I just want to flip that bit. How do you flip a stupid bit? I guess it's an OR. Okay. I guess it's an OR. Value keeps whatever it has, but that flip goes to 1. And then dot 0, and let me check here. Can you do this, Python? Oh yes. So if instead, and so this means that 5, so like this example was wrong because 5 has already the first bit flipped to 1. So 5 should stay 5 here in this case. Okay, so it works. Now I know how to do basic stuff again. So if it's 0, we want to do value, and we want to end it in this case with 0 shifted I times. We want to write a 0 there, and that's it. Or almost. So value has to be a var then, it cannot be a const because we're modifying it. We apply all the changes, and then we do memory dot want put, and we don't care if the key was already there and we are overriding it. It's fine. So this is the address and this is the value, and we are done. And I think this needs to try, and that's it. So now, after we're done with the while loop, we need to sum everything. So I think it's var mem it equals memory dot iterator. Yes, thank you. While mem it dot next gives us an entry. So for each entry, what we want to do is, well, var total equals total is a SUSY. Wait, is this stuff all SUSYs for real? Yeah, it's all positive numbers. Yeah, everything is unsigned. Okay. So total starts at 0. As long as we have entries, we want to do entry dot value, and we want to add that to the total. And that's it. Is this really it? I mean, this seems easy. Programming errors. Oh, I know what programming errors I have. First of all, try std.math fmt.parse int new size. This is the buffer, and the base is 10. So yeah, we need to parse these things. Is that it? pretty much. I mean, well, let's find out which programming errors I baked into this code. Let's keep Python open, might prove useful, I don't know. Documents, AUC, zig, build day 14. There has to be a programming error. Oh yes, thank you. The left and shift, left right hand, oh my god. Or shift must be a fixed width integer type, or right hand must be a compile time known. Must be a fixed width integer type. Okay, that's fine. That actually makes sense, I think. Expected type. Wait. Left type. So what's on the left of the shift must be a fixed width integer type, which is what I just did. Or right hand type must be compile time known. Expected U6 found usize. Note, unsigned 6-bit int cannot represent all possible unsigned 64-bit values. Also, I have to downcast this to a U6. Okay. I mean, it's a bit annoying, but it makes sense, right? Like, this is making sure that what I'm trying to do is correctly dialed into the type system. So this is the final number. Let's see. It's not the right answer, the number is too low. Oh no. So we have a bug in the program. Oh, you know what? I know what the bug is. God damn it. You see this I here, right? Const shift of type U6 is mask.len minus I. I forgot that the orientation. The good news is that now we can get rid of a cast. Yep. Except IP6 found usize. God damn it, where? Int cast in 6. Okay, that's not good either. What is going on? So with the mask here, the problem is the leftmost bit needs to have the highest power. Okay, you know what? Let's do one round and see how it goes and see what it does. So that's annoying. Should I do this by hand? You know what? Can I, how do I print a number in, is it bin a thing? Can I do bin of this? I think it needs 2 parameters, maybe. String object cannot be interpreted as an integer. Oh yes, thank you. which means that this needs to go there, and everything on the left is zeros. Okay, let's do it with zeros then. So 1 0 1 1 1 1 1 1 1 0 1 1 1 0 0 0 1 1 is fine. 0 0 0 0 0. Okay, so this is the correct number. So 0b, this stuff. So I think that this is how the number should be transformed. Let's see what happens if we just run this. Total 0. Okay, no. We are absolutely off. Why? Masculine is 36. It's 36. Should I do a -1? I think the problem is that I need to do a -1 because the first round that we do this, I equals 0. Yeah, I think we have an off by 1 error. Okay, you know what? We know how big this stuff is. It's like 35, right? So it should go. It should be 35, yes. So we want the last one to be 0. So that's one thing. Invalid character. Wait a second. What? Oh yeah, no, wait. I messed up with this input. Okay, this total 0 is scary. That's definitely not the right thing. Print value equals. What am I doing wrong? Which seemed to be fine earlier. Okay, why is it 0? I mean, okay, clearly it's 0 because I'm doing this stuff here. So out of curiosity, let's keep the wrong version. Actually, instead of 35 minus I, it's just I. So this was producing like, okay, this is still 0. Okay, show me the original stuff. Show me the original address and value. Address is this, value is this. Yep. Value after is 0. Oh. I think it's this. Oh, you know what? I'm a moron. This is not going to flip to 0 that bit. This is going to 0 everything. Every single time. Oh man. I'm such an idiot. Because everything has to be 1 except that slot. So this has to be an AND. And this becomes a everything is 0 except the 1. But this has to become a everything is 1 except this slot. So yeah, because it flips every bit. It's not flipping just a bit that we want to manipulate. Out of curiosity, What bit operation do we have in Zig? Let's take a look at the built-ins. I'm not looking, I don't care about the operators. I think when it comes to the operators, we have the normal stuff. But I want to see if there's a bit this, bit that, bit nyek. Oh yeah, look at this. So bit cast, bit offset off, byte swap, bit reverse, accepts any integer type, reverse the bit pattern of the integer value, including the sign bit if applicable. So for example, 1 0 1 1 0 0 1 blah 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 becomes 0 1. Okay, so it really inverts the thing. Can this be useful? Yes, it could be useful, because here's what we do. We shift a 1 there. Everything now is zeros except that it is 1. And then we flip it, and now everything is ones except that there is a 0. Nice. Yep, exactly. Get all ones and shift the 0. Yeah, that's also, I mean, more or less it's the same thing. So here what we want to do is at bit reverse type usize. Yep. Yeah, boy. Let's reverse that Susie. Nice. It doesn't work. Why? I think we're not doing a bad job here. What if I remove this 35 minus I thing? Out of curiosity, still zeros. Why is valued zeros? Is it the OR ring? It's not the OR. Oh, yeah, it's not the OR. It's the AND that is messing around, which makes sense. 23, 19, 8, 6, 38. So it's kinda okay, not completely okay, because rightly so we are messing around with this. So why is our AND not working? Is this not an AND? It's not an AND, right? Because here is 1. Wait, if this is 1 and this is 0, we return 0. If this is 1 and this is 1, we return 1. If this is 0, no, it is an AND. What am I doing wrong? Am I shifting the wrong number of times? No. Is the AND percent equal? Okay, that's a good question. It should be, but yeah, let's double check. So operators are up here, and we have 2 2 2. Bit shift right, bit shift left. Bitwise AND, bitwise OR, bitwise XOR. I think it's the AND that we want. Don't we? 0 1 1 0 0 1. Yep, it's the AND. Do I need a delta? Oh, bitwise not. Oh, is the bitwise not the same as flipping around? Look at that. Why is bit reverse a thing then if you can do the same with not? That's interesting. Oh, there you go. Now it works. So why was bit reverse not okay? Oh, you know what it is? I think I got it wrong when I was reading bit reverse. I think bit reverse is like, it's not flipping ones to zeros, because that's what not does, which for some reason I couldn't have in my brain. I think bit reverse is flipping. Oh yeah, look at this. It's okay. It's like reading everything from the other hand. Oh my god, I'm such a moron. Yes, it's a not. It's what we need. Oh god. Okay, so now this works, and I think everything else works. Oops. Yay. Okay, I don't know why I was so... I'm dumb. Okay, for some reason the seaport's computer system can't communicate with your Ferry's docking program. Oh no, you must be using version 2 of the decoder chip. A version 2 decoder chip doesn't modify the values being written at all. Instead, it acts as a memory address decoder. Immediately before a value is written to memory, each bit in the bit mask modifies the corresponding bit of the destination memory address in the following way. Okay, that's nice. Actually, you know what? I could have somehow expected this. I guess this is now a virtual memory system, right? Like this is an application that is modifying its own memory addresses, and this mask is, it's a bit funky, but this mask is basically what virtual memory does. It's saying, well, yes, you think you have access to all the memory in this absolute way, but actually I'm confining you in this specific subset of memory. Well, usually like the mask is a prefix so that you don't have like everything around, but anyway, funny. Okay, so we don't modify values anymore. Now we modify indices. Immediately before memory is written to memory, each bit in the bit mask modifies the corresponding bit of the destination memory address in the following way. If the bit mask is 0, the corresponding memory bit address is unchanged. If it's 1, it's overwritten by 1. If it's X, the bit is floating. Oh god. A floating bit is not connected to anything, instead fluctuates unpredictably. In practice, this means the following bits will take on all possible values, potentially causing many memory addresses to be written all at once. Oh god, we have like, holy shit. Okay, we have like multicast memory. So for example, consider the following program. So it used to be nice, now it's not nice anymore. I hate X's. X's were nice, now they're not nice anymore. Okay, I think I get the gist of it. I'm gonna mess up the computation, like the algorithm, so many times. But we'll see. The entire 36-bit address space still begins, initialized, blah blah blah, and blah blah blah. This time is 2008. It's 208. Okay. The change seems complex but reasonable. So let's remove this. Now, the mask doesn't apply to value anymore. It applies to address. But now the problem is we need to produce a set of addresses to write to. So here's what we're gonna do. We do this to address. So now this is const and this is var. We do this to address now. And the X is an op when we are modifying stuff. But then after we are done with a first pass where we change the address with the we apply the fixed changes, then we need to do something for each X that we encounter. And this smells of recursion. We can probably make do without recursion, I guess. Maybe, but it would be weird in any case. So let's not do that. Let's just do recursion and call it a day. So what we do here is basically, but we need this function, and we need to give to this function all addresses. We need to give it the mask, which is a 36. Yeah. Oh god, which is this? The 36 enum thingy. You know what? I might need to extract this enum. Oh god, I'll need to extract this enum into a proper type, I fear. Const op is an enum. Is 36 ops. So we need to give it the mask. We need to give it the memory. And then I guess we need to say at which index it should start. All addresses. Wait, what? Why does it need the memory? It doesn't need the memory. Why am I dumb? It needs the address. Wait, no, I am totally dumb. Because it needs to apply the change and then recurse. So that's why we need the memory, need the address, and need the value too. I think this needs to be able to return an error. So let's add a comma so that the signature comes short. Okay. So basically we need to do the put thing in a recursive fashion. And what else? Also, we need to change this, right? Because I think the things changed. So if it's 0, the address bit is unchanged. So now 0 becomes op2. If it's 1, it's overwritten by 1. Which is what we're already doing. Okay, so 0 has been simplified away. 1 still overwrites. X is causing headaches to us. So here's what we do. All addresses has also, I think it needs an index. So here's what we do. We give it an index, and what it does is if mask at index is a nop, well, which in this case nop is not a thing anymore. Let's call it, I don't know, let's call it X so that it has a, because previously X was a nop, now it's definitely not a nop anymore. So if mask ADX is X, then we want to do want to call all addresses twice. Mask memory IDX +1 address needs to be modified. New address value, and new address is gonna be oh, that's nice. So in one we have to put a 0 there, and in the other we have to put a 1 there, so we can reuse this thing too, which is nice. Why did I fail to copy? Oh god, what did I do? I pasted instead of copying. Remove the equals. So in one we are basically saying that bit, how much do we shift? Shift is still this, I think. Yep. 35 minus IDX. In one case we put address to 1, that bit to 1, in another case we put it to 0. We do both. And then what do we do? So this keeps branching out, putting x at all possible values, but we are missing the base case, right? Where we need to actually put stuff inside. So what we want to do is that if we reach the end, if we are at the bottom of the recursion, and there's going to be a bunch of, like, there's going to be a lot of calls that end up being part of the recursion. So if, I guess, if IDX equals, hey Matt, thank you for the subscription. Oh, you found it, Neobide. Okay, I'll take a look. Oh god, how can I put this back there? God damn it, Safari! Oh, I can do this. Just, oh, I found a way of cheating. Okay, I'll take a look later. Hey, yeah. Okay, so if we are at the bottom, so if index is 35, we put the address and we are done. Actually, this should go above so that we don't overflow. So if index 35, we put this stuff and we are done. Else if expected. Oh, but we can do this. Boom, boom. No, we should be able to do this. If x35, do this. Else if. Okay, so if the index is 35, which means it's the end, we put the address, or we put the value at address because we know we have scanned through everything. Oh yeah, you said, oh, here, sorry, I missed your message from before. You didn't send other messages. Sorry, this is intense. It's catching all my attention. I think we're done. Here's one thing that I might be not do right. I think maybe this needs to be a pointer. Maybe it's a good idea not to copy the hash map around. Probably a good idea. Masks can be copied, so that's fine. Oh, I know that it has to be a pointer, because otherwise this would be const and I wouldn't be able to modify it. Oh, that's so nice. I'm at 9. I wish I had $5,000. Well, AOC any percentage speedrun, if any percentage is fine, then actually 0% is fine too, because I think then you just, I don't know, you just open each page not even read the description and then you click the end. I don't know. In any case, are we done? I think we're done. Why am I oversimplifying in my brain some step? I feel like the... Oh wait, I need the one call. So the one call is here, where we say then all addresses mask. Oh, wait. Where does this go? Because this is an if else. This goes here, right? Yes. All addresses mask. Pointer to memory. Come on, Sublime. Index is, we start at 0. Address is our address. Value is our value. And this should recurse. I don't know. Is this gonna poop itself? Okay, compile error. So let's go. Error ignore, consider using try. Good point. And don't tell me. You need to do it here too. Next. Cannot resolve inferred error set. All addresses is not fully analyzed yet. Oh yeah, that's annoying. So it's recursive and it's hard to understand what the error set is. But it's fine. Just say it's any error. I don't care much. Total 0. Perfect. Precisely the right answer to everything. God damn it. There's clearly something wrong. So here's what we can do. Let's make this branch a bit more complicated, and let's take a look at what we are trying to write every single time. What? Oh, I'm dumb. I'm dumb. This is not an else if. Oh god. Yeah, well, if I don't encounter a X, I need to move forward. I mean, I'm not just gonna stop. This is why I was... I need to move forward, which makes sense. So, I guess it's var I equals idx. While mask index I is different is let me think about it. You know what we can do? We started index, and we in the while loop we could do this while I is lower than mask.len. This is so ugly, but whatever. I plus equals 1. If mask I is different than X, we continue, so we don't do anything. But if if instead max equals I is an X, if we found our match, then we use I to do our stuff, and then we break, because we know we do it only for one X, and then the recursion will kick in. So we start from the index that we're given, and we keep scanning, we keep moving forward until we find an X. When we do find an X, we do the shifting stuff, and then we stop. This could even be a return, to be clear. Is it better now? Okay. Okay, that's a lot of spam. I don't know. Test it. That's not the right answer. It's too low. What? Am I missing something also? Yeah, I skipped a bit of stuff. Maybe I should have read it more, but so it causes more memory addresses to be written at once. For example, consider the following program. When this program goes to write to memory address 42, it first applies the bit mask. Yes. And after applying the mask, 4 bits are overwritten, 3 of which are different, and 2 of which are floating. And then for each of the floating ones, tries yes. And he finds all the addresses. Next, the problem is about to write memory 26 with a different bit mask. It results in an address with 3 floating bits, causing writes to 8 memory addresses. The entire 26 still begins initialized to the value 0, and you will still need the sum of the values left in memory at the end of the program. In this example, the sum is 208. So what are we doing wrong? Let me think. Where could we have bugs? Where could we have bugs? So this thing, while I was looking at my output here, so you know what? Let's do the thing where again we just keep one line. Are you serious? Is this enough to is this enough to find my bug? What the hell, man? What did I do here? So this first case already doesn't work? Why? Why are we never reaching this? I know why. Because with this stupid thing, I know why. Because with this stupid thing here, it happens that if we keep scanning, we are past the final X, we keep scanning until the end, but then we don't commit, we don't hit the end. Like we only hit the end here if the final index is an X. Because otherwise we never call this with index 35. So what we want to do is, instead of doing this, we want to say, if you never, well, it's not even an else actually, is if we got past this while loop, so if we never applied any change, it means that we are done and it's time to commit. We never found any X, so we can commit, we are done. I'm finally thinking this is gonna work. Okay, so this is I mean, this is reasonable. There's a bunch of things. So many bugs. Yay, right answer. Honestly, it wasn't that hard. But as usual, a bunch of bugs in the code. So retrospective. Retrospective is you kind of need to remember that not exists as a binary operator. That helps. I don't know why I thought that bit reverse was doing the not thing. Well, at the end of the day, you know what? You're basically just catching the fact that I don't do much bit fiddling. That's it. I think that people that do more bit fiddling would get this right first try more easily because they know what they're doing. In any case, yeah, not hard. Like, you just remember what the operations at your disposal are, think about it a little bit, and then everything works out. Enums here are nice. This switch as a expression is nice so that we can set mask to what we want. Using an auto array hash map for the memory, it's also probably a good idea. When you start having floating bits, you start occupying more of the space, I guess, but it's still probably not contiguous enough to be worth it. What else? Recursion, that's fine. Recursion is fine, indices is fine. Address is fine. Problem was, yeah, I needed to think about my cases a little bit better in the recursion, but that's fine. Also, cute how they basically helped you. The first half of the challenge basically made you come up with these two expressions, which then you can reuse later on, which is nice. So that's also kind of nice. I have to say, this one was pretty straightforward. I agree. This was straightforward, kind of nice. No weird parsing stuff. It was fun. So I'm happy about this. So I'm gonna cut here the recording for YouTube. So YouTube, see you next Advent of Code.